Welcome to the new lecture of population balance modeling. Now, population balance modeling is a very important concept in any kind of polymerization reaction, and this is also very useful for predicting the behavior of in situ polymerization and further the developed polymer which may be produced in due course of any polymerization process. Basically, it deals with the various kind of chain, development of chain, monomer behavior within this polymer mass. So, we will start this population balance modeling in this particular subchapter. Now, before we start this thing, let us have a brief look about that what we discussed previously. We discussed about the heterogeneous polymerization. Apart from this, under the subhead of heterogeneous polymerization, we discussed the precipitation, concept of suspension polymerization, and discuss a brief about the emulsion polymerization. Now, emulsion polymerization is a very vast segment in which with the help of emulsion we used to form the polymerization process, and we will seek the help of this emulsion polymerization concept in this particular chapter. So, we are going to cover the population balance modeling in this chapter. Apart from this, we will discuss about the various calculations attributed to the physical properties and phase equilibria. Both these things are a very important concept in polymerization step, and then we will discuss all these things with the help of the emulsion polymerization concept. Now, let us have a look about the concept of population balance modeling. Now, population balance modeling is a widely used approach to describe the growth of polymer chains. It also explains the concept of chain agglomeration and breakage. Now, before we proceed further, let us have a look about this particular concept. As we know that when whatever method we follow for the polymerization process, it consists of development of chains within the polymer mass, within the reaction mass. So, whenever we talk about this, the control of these chains are extremely important. Now, control parameter also attributed to the molecular weight distribution. As we know that the molecular weight distribution plays a very vital role in predicting the property of polymer. Sometimes it is attributed to the viscosity, sometimes it is attributed to the glass transition temperature. So, it plays a very vital role in deciding the final outcome of the polymer. So, whenever we discuss this particular approach, then our point of focus should be like this, that what is the fait accompli of those chains being developed in the reaction mass. When we carry out any kind of a polymerization reaction in a reactor, then my focus of attention would be that how many monomers are participating, what is the fate of chains, what is the length of those chains, what is the molecular weight of those chains, so etc. So, there are so many things should come into our mind. So, that is why whenever we wish to predict the behavior of final outcome, maybe the polymer, maybe the polymeric system, etc. So, population balance modeling comes into the picture. So, see, it also seems the perfect concept of accounting for the changes in the polymer chain length. So, whenever we talk about the molecular weight distribution, then polymer chain length, they play a very vital role in deciding the fate of those molecular weight distribution. So, slight change in the length of a polymer chain, slight change in other aspect of those chains may adversely or favorably affect the molecular weight distribution. And moreover, you see that these polymer chains are sometimes overlapped each other or entangled with each other. So, whenever we deal with the bulky chains, then sometimes the movement of those chains would be restricted because of the higher molecular weight or higher weight. So, it ultimately affects the final property of the polymer. So, therefore, in view of this, one may be interested that what is going on within the reaction mass, and what are those polymer chains how these polymer chains are affecting those polymer mass. So based on this, the population balance modeling, it came into the existence for the help of the predicting the behavior of polymerization process in totality. So in other words, we may say that the population balance on any system is usually accountable for tracking the number of variables. Now you see, there are so many variables present in the reaction mass. One may be the monomer, sometimes it may be the drops, sometimes it may be with respect to the bubbles, sometimes it may be with respect to the chain, sometimes it may be with respect to the catalytic behavior. So there are so many variables are associated with the polymerization reaction. And you know that these presence or occurrence, this may tutor the behavior of polymeric system. So that's why, keeping in account of these variables, these different parameters, etc., those who are directly affecting the behavior of polymerization, directly affecting the final outcome of the polymer product, the population balance modeling is extremely important. Now question arises, what is the basic genesis of this population balance modeling? Now this usually follow the dynamic evolution of particle size distribution, sometimes referred as PSD in a particular process. So see, this is you can correlate that one single monomer may attach with another monomer to give you two monomer joined together, and then the series of these monomer, when joined together, they form the polymer chain. So by this way, there is a dynamic evaluation of various chains. Similarly, this is the dynamic evaluation of the particle size distribution. So a population balance approach is commonly employed to predict the behavior of those dynamic evaluation concept in any kind of particle size distribution. The distribution of the particle is usually considered to be continuous in the volume domain, and it is usually described by the number density. Usually it is a function of V and T. Now you see in this particular figure, where there are two type of agglomeration agglomeration are presented. Here this is one mass, another is collision. Now there are two concepts. One is that either it directly collide with this particular mass, and this is unsuccessful collision. Now once it is a successful collision, then there are again two options with respect to this primary agglomeration. It may successfully collide and it may attach to the surface of this particular particle, and similarly it may have another option that it may have a successful collision. So this is you see that this is the single layer of primary particle via primary agglomeration, and whenever you may have a sufficient number of other particles, then there may be a chance of multi-layer formation while the secondary agglomeration. So by this way you can predict and you can see that there is a evolution, there is a successive evolution of different type of particle sized. Now this VTdV, this represents the number of particles per unit volume within the differential volume set, and this may be this V may be represented as V plus dV. For the dynamic particular system, the rate of change of number density function with respect to time and volume is usually calculated by different non-linear integral differential population balance equation. So let us have a look about those differential population balance equation. So, this is the mathematical representation of this population balance equation. Del T and Vt over del T is equal to V, that is the V starting V, and then you are approaching to the maximum volume, then it is beta UV, U, G, UN, UT, DU, plus you may have a minimum concept, then V, K, V minus U minus UT and UT DU minus N VT G and VT. Then let us see the impact of minimum to maximum. Then V minimum to V maximum and K U N U T D U. Let us represent this particular equation as one. Now the first term on this right hand side, this equation, this represents the generation of droplets in the size range V plus dV due to drop breakage. Now drop breakage sometimes plays a very vital role in deciding the fate of polymeric system. Now this beta UV, this is the daughter drop breakage function, and usually accounting for the probability that a drop of volume V is formed via the breakage of a drop of volume U. So this is one way to predict the equation. Now in this previous equation, this function u, this denotes the number of droplets formed by the breakage of a drop of volume U and G U. This is the breakage rate of drops of volume U. So if you see, this is the first term of that particular equation. Now if we talk about the second term of the right hand side equation, this describes the rate of generation of drops in the size range of V plus dV. This is maybe due to coalescence of two smaller drops, and KVU is the coalescence rate between two drops of volume U and V. So if you see that when we talk about these drops, that means the agglomeration or coalescence of two monomer molecules. Sometimes these monomer molecules, these are the two they make adjoint with the other two. So this reflects their behavior in this particular aspect. Now the third and fourth verse, they reflects the decrease. Third and fourth one, they reflects the decrease in disappearance rates attributed to decrease in breakage and coalescence respectively. Now, this particular concept is again very important in view of this, that sometimes there is a formation as well as there is a dissociation of all these chains. So, sometimes it may appear that due to this particular concept you are having the utmost attention towards this population balance modeling. Now, this the equation which we discussed earlier, this will satisfy the initial conditions, say t is equal to 0, then n v 0 is equal to n naught v. This may be reflected as equation number 2. Now, this n naught v is the initial drop size distribution, is the initial drop size distribution of dispersed phase. Now, you see that when we talk about the dispersed phase, that means the emulsion polymerization, it comes into the existence. So, these two equations, or apart rather, the equation number 1 is very important equation related to this drop size distribution and the polymeric system, and especially taking into account with the dispersed phase. Now, let us have a brief outlook that the concept of drop breakage process. Now, the drop breakage in the turbulent flow field can be caused by the viscous shear force, by the turbulent pressure fluctuation, and by the relative velocity fluctuation. So, sometimes in the polymeric system you need to incorporate these type of approaches to enhance the rate of polymerization. So, that is why this particular approach is sometimes extremely useful, and if you recall that during the emulsion or a suspension polymerization process, when we discussed agitation and the flow rate, both play a very vital role in deciding the fate and deciding the number and size of the polymeric chain being developed in due course of time. So, as a drop breakage, this happens sometimes due to the viscous shear force. The monomer droplet is the first elongate into two fluid lump system divided by a liquid cord. You can see that this is the concept of a drop breakage. There is a big drop and it can be breaked into the small particles, and sometimes these small particles may go for the coalescence to give you the bigger one. So, let us have this particular concept related to the breakage. So, there are thorough breakage. Now, sometimes the deformed monomer droplets, they split into two nearly equal sized droplets and corresponding to fluid lumps and a series of smaller droplet corresponding to the liquid threads. So, this is considered as a thorough breakage. So, the genesis of this thorough breakage is that splitting into nearly two equal size of drops. Another is the erosive breakage. So, when the relative velocity of this particle is similar to that needed to make a drop slightly unstable, a number of tiny droplets, they are separated from the original one, like we discussed in this figure. So, this drop breakage condition is sometimes referred as erosive breakage. Now, it is considered to be the dominant mechanism of low coalescence system, and that exhibit a characteristic bimodality in the particle size distribution. So, that is why this particular concept is extremely important while discussing when drop size breakage, and equally important in emulsion polymerization as well as suspension polymerization. Now, if you recall, in the suspension polymerization we are more and more concerned towards the formation of small drop at early stage. So, when you perform the agitation, then this type of a concept play a very vital role in deciding the final outcome of those polymer product. Let's have the things related to the suspension polymerization. Now, here you see that the thorough breakage, where you see that this drop is breaked into two nearly equal sized of drops. When we talk about the erosive breakage, then you see that there are dissimilar type of things happened in this approach. You may see there are small particles, drops, and then a bigger one. Sometimes this we discussed that the coalescence is provided by the continuous liquid film. So, sometimes this particular approach is like this. You may see that here is a formation of a film, and thereafter you may experience the bigger one or bigger drop size in the suspension polymerization. Similarly, if we see, sometimes we may see that immediate coalescence. Now, immediate coalescence is that two equal sized drops, they are combined together to form this one, and then over the period of time they may form this type of bigger drop. When we talk about the suspension polymerization, this type of approach is sometimes very trivial one, because sometimes it may promote the formation of agglomeration, thereby the highly viscous polymer gel within the reactor system, and that may create a future problem, and sometimes it may create the problem of damage to the reactor, or sometimes damage to the impellers of agitators, etc. So, this type of things should be addressed clearly when we discuss this drop breakage process under the head of suspension polymerization. So, when we talk about the modeling of these drop breakage process within the head of polymerization process, the first approach is to modeling the drop breakage process in liquid-liquid dispersion. This was based by the Weber number. Now, it is used for the measurement of mean drop diameter. You see that we discussed a lot of different sizes of drops in this particular slide. So, this it is used to measure the mean drop diameter as well as the maximum stable drop diameter for breakage to occur, and a minimum drop diameter above which coalescence occur. So, this particular approach is extremely important while discussing the things. Now, let us have a look about the modeling concept of this drop breakage process. Now, this the modeling of drop breakage rate is expressed in terms of breakage frequency, sometimes referred as omega b v, and respective Maxwell efficiency term. So, it is represented as G V e to the power minus lambda b v. Now, this lambda b v, this is the ratio of the required to the available energy for drop breakage to occur. So, because you see that when we discuss about the drop breakage concept, then some CO motor, some energy for etc., this is required to carry out this particular process. Now, let us assume that a drop of volume U breaks into NDA daughter drops. Daughter drops are small size tiny drops which we discussed in previous figure, and NSA, this is the satellite drops. So, the daughter drops and satellite drops are normally distributed about their respective mean values. So, respective mean values are sometimes referred as, these are the respective mean values. Now, there is a need to derive an expression for the number of drops S in volume V generated by the breakage of the drop in volume U. So, we need to develop one mathematical equation for the same. So, this equation can be represented like this: beta uv, this is equal to NDA 1 upon sigma, that is the mean which we discussed, 2 pi square upon 2 sigma dA square plus NSA satellite bracket 1 upon minus V minus VSA square upon 2. So, the daughter drop number density function UU V, this it should satisfy the following number and volume conservation equation. So, let us have those number and volume conservation equation. One is from 0 to U, and second equation is dV is equal to 0. So, these are the number and volume conservation equations, and these equations are quite useful for further calculation. So, the mean volume of daughter and satellite drops, mean volume of daughter and satellite drops usually formed by the breakage of a drop of volume U in terms of NDA and NSA. It can be represented as DA and DA plus upon RD, and SA satellite, that is this is the daughter one, and the satellite one is U upon RD and DA plus NSA small rd, this is equal to DA upon SA. This is the satellite one. Now, here NDA and SA, sigma DA, SA and RD, they are the model parameters. So, by this way we can start this modeling of those parameters. Now, there are two different mechanisms, because when we talk about the modeling of this drop process, and especially when we discuss about the drop coalescence process, there are two different mechanisms have been postulated in various literature to describe the coalescence of two drops in turbulent flow field. If you recall that in this discuss, first we formed the two drops and then the coalescence of these two drops in turbulent flow field. So, the first believes that after the initial collision, the two drops, a continuous phase liquid film is stuck between these two drops, which stops them forming coalescing. Now, this is the small once they coalesce, then there is a formation of a small thin film in between these two drops. So, thereby this prohibits or inhibits the formation of coalescence. Now, due to the presence of attractive force draining the liquid film can occur, leading to drop coalescence. So, sometimes when these two drops they form a thin film, then sometimes the attractive force play a very vital role. It snatched away this liquid film being formed in between these two drops. Now, if the kinetic energy of the triggered drop oscillation is greater than the energy of adhesion between the drops, the drop link is interrupted until the liquid film is fully drained, so that the coalescence may form in due course of time and you may experience the bigger sized drop. The second concept attributed that coalescence process implies that the instantaneous coalescence happen as the relative velocity of two colliding species decreases at the moment of collision reaches the critical value. So, whenever these two are combining together, relative velocity decreases and thereby they form this one. So, it is just like this and this one. So, this means that the drops will coalesce if energy of collision is greater than the total drop surface energy. So, these two things are very crucial. Now, sometimes when we need to express the things, so the drop coalescence rate it can be expressed in terms of collision frequency, sometimes referred as omega b Vu, and a Maxwell efficiency term which we described earlier, and the equation can be represented like this: k u omega c uv e to the power minus lambda c uv. Now, where this lambda c uv is the ratio of the ratio required to available energy for the drop coalescence to occur. So, in this particular lecture we discussed about the concept of population balance and its efficacy in predicting the behavior of various particles or various chains being developed in the polymerization process. We discussed about the drop coalescence process. We discussed about the various concepts of formation of a drop and then adjoining and the formation of the agglomerates in these drop coalescence process. In the next lecture we will discuss about the physical properties and the phase equilibria concept related to the polymerization system. Thank you very much.